Hi, I'm Chris Brown, and this is a lecture on machining process variables and chip formation, part of a course in axiomatic design and manufacturing processes. This is section 2.15a. All right, so PVs and DPs in machining. So PVs, of course, are the process variables, the input to the process. Generally, we think in machining of at least feed, speed, depth of cut. Also tooling and coolant are important, and there's several more as we'll see. And this is basically how you make the part. The design parameters are the elements of the physical space, and these are essentially the outputs of manufacturing. And it's the surface finish, the shape, and what kinds of tolerances you can achieve. And this is what the part is like, of course, when it's done. So it's kind of a mixture of process variables in the workpiece that go into the manufacturing process and produce the design parameters. So this is what we've been talking about previously, just putting it in the context of machining. So more on the process variables. So these are independent variables or parameters. And again, feed, speed, depth of cut. We could also talk about the width of cut, as we see in this example of milling, and the tooling. And so there's quite a lot of different kinds of milling tools that you could have. And then it's organized hierarchically. So we have machining, milling, and then perhaps end milling. We notice, of course, that the PVs influence the design parameters and the cost drivers when we're looking at things like the manufacturing process development, FRs. Like tool wear and machining time. So the design parameters, the NPDs, the new product development DPs in machining, are what the customer pays for essentially. So form, tolerance, surface quality. So the machining process, all right, so in all of these machining processes by chip removal, we have similar chip formation mechanics. Actually, we could extend this to different kinds of abrasive processes as well. So turning, milling, sawing, drilling, tapping, all have similar kinds of chip formation mechanics. So as we look at the most common examples, milling, all right, and actually the first milling machine, according to some history, was made in New England by Eli Whitney when he in Connecticut, and turning, and there's an example of a close-up of turning. So we have to create some kind of relative motion between the cutting tool edge and the workpiece. And in milling, the workpiece is essentially fixed to a table which moves in X and Y. This is the workpiece here, and the cutting tool rotates, and it's rotating this direction. You can see a chip forming there. And in machining, the workpiece is spinning and rotates in a spindle, whereas it's the tool in milling. And then the cutting tool is mounted to a carriage or a turret and then feeds along in this direction. Whereas it's the workpiece that feeds in milling, it is the tool that feeds in turning. So these terms that are used in machining can be confusing. And the definitions can sometimes depend on the context. The same word in different contexts can mean different things, and different words can mean the same thing. So watch out for the context. Never be afraid to ask somebody what they actually mean by it. And it's machining, the tool, the tooling, the feed rate, the feed per revolution, and then there's the work holders, the tool holder, and it's so there can be quite a lot of vocabulary there, and some of it is specific to different kinds of organizations. I know one company actually makes a verb out of lathe, and so instead of calling it turning, they call it lathing. All right, so in turning, the tool motion is in X or Z. So you might move in and do some sort of facing operation. This is a turning operation where we're changing the diameter from this large diameter to the smaller one. The C axis is the rotational axis, and the Z is along this way. And the depth of cut gives us a change of radius. So this would be the depth of cut from here to here. So the change in diameter, of course, is going to be twice the depth of cut. And milling, so here is the table that moves in X and Y, and then the tool moves in Z in a conventional kind of milling machine. And you have the feed, which is how the workpiece is being fed into the tool in X or Y. The speed, which is how fast the spindle, which is up here, is rotating about the Z-axis. The step over is how far I move between successive motions or feeds of the tool. And then the depth of cut is how deep the tool is engaged into the workpiece during milling. So the primary process variables, as we said, are essentially the tool geometry and tool material, so the tooling, feed, speed, and depth of cut. Now the feed is often context specific, as we've talked about, so it means different things in turning and in milling. The speed as well can be the surface speed in inches per minute, feet per minute, meters per second, something like that. Or it could be rotational, RPM and radians per second. Depth of cut, all right, it's different in turning and orthogonal machining. Now, orthogonal machining we haven't mentioned yet, but that's usually just used for modeling the machining operation. And then there's milling, and the depth of cut can be radial or axial. The tool geometry can be quite complicated, and so there's different angles here as shown in turning, and of course when we move to something like tapping or milling, the tool geometry can get even more complicated because we have flutes and different cutting edges. But this is so the basis, and there is the back rake angle, which is commonly called the rake angle when we move to to orthogonal machining. But of course there's many different orientations we can be looking at. There's a side cutting edge angle, in cutting edge angle, and the back rake angle. So there's many different angles that can be defined there. Just be aware of the complexity and know which angle we're talking about. Most of the time we're going to be looking at just what we call the rake angle, which is the back rake angle in this depiction. The tool holder, and then there's the insert holder. So this is a cutting tool insert. It's hard to see. We'll see more of these. It's being held in here by this thing, which is on the tool holder. Also note that the insert material often is like tungsten carbide cobalt when we're using a cutting tool insert. Some tools are still made out of tool steel when they're monolithic and you're not changing this so much. Or it can be brazed in tungsten carbide cobalt. This one is changeable. And often there's a titanium nitride coating or some other coatings. Actually, the coatings can get quite sophisticated. So the geometry is even more complicated than we're just looking at. So we're looking at the new product development PVs in a cutting tool. So much of what we're going to be looking at here would be useful if we're actually designing these tools or designing the machines or some special machining process. So here's an example of a tool insert, and it's got a coating. It's titanium nitride. Mostly you see these gold coatings and they're titanium nitride. This reduces the friction and the wear resistance. So this has got a little sort of raised portion around the side. This is a controlled contact edge. And then this thing that sticks up is a chip breaker or a chip control feature that's trying to keep the chip under control and keep it from wrapping around the workpiece. So other PVs, the highest level we're choosing, is it milling or turning and what kind of milling machine. For example, a mini mill or an SL10, which are machines that we have in our lab. And then we've got the tool holder and the sort of the holder's holder and the cutting tool insert, often with ceramic coatings. Fixtures that are holding the workpiece, this can be important. The spindles and that turn the workpiece in the lathe or the tool in the milling machine, those can also have an impact. The CAM software, computer-aided manufacturing software, that selects the tool path and sort of runs the machine tool, can optimize different things depending on what the customer wants and what the vendor has available. And so sometimes it's tool life that's optimized, sometimes it can be machining time, and then, of course, the type of operation. The coordinate system that's chosen can often make a difference too, so there's quite a few PVs. As a matter of fact, there's too many, because if we consider them all, we have a distinctly non-square matrix. We took a look at what the DPs were that we needed, and those are relatively few. So why so many PVs? Well, we have certainly what's called a redundant design, and it may be a coupled design. So usually in these cases, what you try to do is hold as many PVs constant as you need in order to arrive at a square matrix. And then decide, you have to decide which ones you want to adjust and which ones you want to hold constant. And we'll have an example of that actually later in this course. So just thinking about deformation mechanics, and this is kind of an important point. So metals are usually crystalline, and crystals deform by line or screw kinds of defects in the crystal that's removed through the crystal lattice, like wrinkles in a rug, and this is how they deform. Now, everything deforms in shear. This is the basic deformation mechanism, and it's powered by this dislocation motion. So in 1944, Eugene Merchant actually published a paper on metal cutting, noting for the first time that the chip forms by shear as opposed to some sort of peeling off thing. And this was a turning point in people's understanding about machining by chip formation. So for understanding the deformation in mechanics, deformation mechanics and machining, so chip formation is really the basis for the scientific understanding of sort of the selection of process variables, which come from like the chip load, and this is what's generating the forces. And so then you have the power, you have the challenge of maintaining tolerances as things deform, and things heat up depending upon the force and the displacement. And so this impacts the fixturing of the tools and the workpiece. And so what we're going to be developing is some understanding of the chip load and the forces and what impacts that. And so we're going to be looking at an analysis of the machining process. A typical question that you sometimes get from the factory floor is, why doesn't the new stuff or the new material, actually the grammar usually isn't as bad as I have it there. Let's give the factory floor people a little more credit. So why doesn't the new stuff machine like the old stuff? And that's kind of the question that's one of the main kinds of questions you get asked. Let's go. All right, why doesn't the new stuff machine like the old stuff? And you can look to the chip for the answers. So if the chip is getting thicker, there's, and this is usually an indication of, well, this is always an indication of greater forces. And so what might this be coming from? And so it could be the friction somehow has gone up. And so this might be the lubricant, or the coating's wearing off, or the coating on the tool isn't so good, or maybe the workpiece material has changed somehow so that it has a higher friction coefficient with the tool. So there's also could be a decreased effective rake angle, maybe due to wear or maybe due to some sort of positioning problem. And this will also result in thicker chips. And then another thing here, sort of parenthetically, is an increased tendency of the material to work harden, will also result in thicker chips. So here's a straight down view on turning, and so this will be our stepping off point to getting into some of the theory here. So we have the tool, which is feeding in this way. This is the rake face of the tool that we're looking straight down on. So this is the cutting edge of the tool that we're seeing. Now later, we're going to be looking at a cross-section of this, and the cutting edge will become a point, and the tool rake face will become a line. But the tool is feeding in this direction, the workpiece is rotating like this. So the chip is forming here in this kind of overlap region between the tool and the workpiece. That's what we're seeing. And the uncut chip thickness, and this will be using in some equations, T1, is shown here, and it's perpendicular to the cutting edge of the major cutting edge of the tool. So the chip is forming primarily along this edge, but also a bit on the nose. And so when we take a cross-section, we're going to be looking at orthogonal machining. It's plane strain, as I said, perpendicular to the cutting edge. The depth of cut is essentially the uncut chip thickness in orthogonal machining. And this is referred to as the feed in turning, and can be referred to as the feed in, that's a function of the feed. And in turning, and can be referred to as the feed in orthogonal machining. This orthogonal machining essentially ignores the tool nose. And let me go back here to this slide. So this region in here is largely the plane strain region. The tool nose and out here at the free surface, those are different kinds of conditions, and they're not in this model. And so you might wonder, well, this is where the surface is forming, and our model isn't showing that. Well, what our model is showing is what most of the chip is doing, and so this is responsible for most of the loads. So let's see, feed ignores the tool nose, often ignores the tool nose radius, as we'll see. Now, you can find online some nice videos of chip formation, and you can actually see some of the things that we're going to be diagramming here. So I recommend you go and Google chip formation in machining, and or try this link here. All right, so the shear angle in orthogonal machining. So here we have, this is the rake face of the tool, all right, and the rake angle is the angle between perpendicular to the direction of tool motion, so the tool is moving in this direction and is creating a new surface here, and so this is the rake angle, so that's the normal to the tool velocity, and the rake face of the tool. So this is the cutting edge now, that is now a point. This was a plane in the previous diagram, is now a line. The relief angle is over here, we're not going to be using that. But the chip forms here on the shear plane. Now, it's obviously a zone. If it were just an infinitesimally thin plane, then here's the undeformed material coming up and suddenly turning into a highly deformed chip. The material deformation in the chip is usually over 100%. And so it can't obviously do that instantaneously, because then it would have an infinite strain rate. So there's some finite zone. Now, as we'll be developing in the next lecture, the shear angle is quite important to the forces. As we talked about, the chip thickness here, T2, is related to the force, and if this is getting thicker for the same uncut chip thickness, then it means that we might have a change in the effective rake angle or an increase in the friction here, and we'll be seeing how that works, or perhaps some change in the nose, which is idealized here as sharp. So this uncut chip thickness T1, it's the depth of cut in orthogonal machining, and as we could see, I think from the last previous slide, when we look here, this T1 uncut chip thickness, in order to convert the feed, which is in this direction, feed per revolution, into the uncut chip thickness, we need to use the side cutting edge angle, the cosine of that. So if the side cutting edge angle is 0, the feed is exactly the uncut chip thickness. But if you go in with a 0 side cutting edge angle, you may have trouble with the chip control. So let's go back to where we were. All right, so for modeling a turning operation, we need to modify T1, the feed, by the side cutting edge angle, cosine of the side cutting edge angle to get T1. So as I said, the chip forms here in the shear zone. Now this relationship, let's go back, this relationship is purely geometric. So this relationship for the tangent of phi is based on the chip thickness ratio, which is T1 to T2, and the rake angle. Now, one of the interesting things about machining is that the system is essentially free to choose its own shear angle. In other words, I push against the workpiece with a tool, and the chip sort of does what it wants. Actually, I'm pushing, if we look carefully, I'm actually not pushing against the workpiece. I'm pushing against the chip. The tool actually, in this idealization, only touches the chip. The chip is forming by shear here, as we said. And now this angle, so the system is essentially free to choose its own angle. So this, as we said, is depending, as we'll see, on the rake angle and on the friction conditions here. So this is a purely geometric relationship to give us the tangent of phi. So if we measure if we know what T1 is from our feed and side cutting edge angle, if we're doing turning, and we can then measure T2, and we should know what the rake angle is, then we can calculate what the shear angle is, just from geometry. It doesn't matter what I'm cutting. This could be a knife scraping butter, and the same equations would apply. In fact, the same sort of kinematics apply, and you can see if you're scooping ice cream, you're creating chips, and it's also shearing, and you can see the shear lamella forming with that, or scraping butter, for example. So this development is actually not so difficult. I'm going to leave that as an example, but try to get you started on that should you want to give it a try. So the trick in this is it frequently is in these kinds of forming problems is to find triangles that maybe share a common side. So if we take a perpendicular to the cutting direction here that intersects right where the chip is forming, we have a triangle there and a triangle here. Now these triangles share a common hypotenuse because that's a right angle and that's a right angle. And so we can set up then an equation where we have these two things being equal. This is T1, this is T2, and then we can develop that relationship for the shear angle, which is here. And so there's the two triangles in another depiction. And so this is the shear plane here, the border between the red and the blue, and the chips going up that way. And the undeformed materials coming into the zone this way. So if you want to try a little example, here's, I've just put in some numbers, and here's the feed, the side cutting edge angle, there's the shear angle, there's the rake angle. So it's an example problem, and this shows the results. The green is the given, and the black is what was calculated. And it turns out that the shear angle is 26.5, so you can give that a try and see if you can come up with the same answer.